In this video lecture, we'll be studying about the logical operations. Let us first understand what are logical operations. We know that a byte is composed of 8 bits. In a computer, a word can be made up of multiple bytes. So for example, a word may be 2 bytes, 4 bytes, or 8 bytes, or as in many modern computers, a word may be made up of 16 bytes. Now, most algorithms can operate on the whole word. That means they can operate on either 4 bytes or 8 bytes or 16 bytes. But there are occasions when an algorithm has to operate on the individual bits or on a group of bits. So it may be that in some case, a particular bit has to be changed from a 0 to 1 or vice versa. In such cases, we use what are called as logical operations. Now, logical operations are used to operate on bits and they can be used to change the individual bit values. And that is why we say that logical operations are also called as bit manipulation operations or bitwise operations. Most programming languages like C, C++, Java, C Sharp, Python, and many others, they support logical operations, bit manipulation operations, or the bitwise operations. Let us see which are the logical operations we'll study in this lecture. The first is a left logical shift operation, which shifts bits to the left in a binary number. The right logical shift operation can shift the bits to the right. The third unusual type of operation is a right arithmetic shift operation. We'll see that this operation is needed to shift bits to the right, especially when we are dealing with negative numbers. Let us start with the first example of a left logical shift operation. We are given here a number 23, which is in the decimal system, and we have converted this into its binary equivalent, which is 10111. We will see step by step how to carry out the left logical shift by one bit. So we'll shift the bits of this number by applying the left logical shift operation, and we'll shift it by one bit. Now here is our original number A. We have shown the bits in separate boxes here. So our original number is 10111. So if we start from the least significant bit, this is our LSB, and if we start from the least significant bit and move from right to left, our bits are 11101. So here are the bits 11101, and since we want to make it a group of 8 bits, we have padded this number with 3 leading zeros. We know that putting leading zeros does not change the value of the number. Now let us shift these bits to the left by 1 bit. Now the way it will work is this. Starting with the least significant bit, we copy the least significant bit into the next higher position because we are shifting the bits to the left. Then we take the next bit and we shift it. So this one bit, the least significant bit, comes into a higher position. The next bit comes into the next higher position, so shift it to the left. Originally this bit, we can see that this bit was initially in a position where the weight is 1. This bit was in a position where the weight was 2. This was in the position with weight 4, weight 8, weight 16, etc. So the bit which is in the weight 2 position, it has been shifted into the higher position, shifted to the left by 1 bit. Similarly, this bit is shifted to the left by 1 position. So we just copy this bit here. This bit 0 is shifted to the left by again 1 position. This bit is shifted to the left by 1 position. Similarly, the bit 0 shifted to the left by 1 position. This is our bit 0, and this bit 0 is again shifted to the left by 1 position. Now observe what happens to this. This bit 0, which is the most significant bit in our original number, this bit is 0. There is no position where this can shift, and therefore this bit simply falls off, or we say that this bit is discarded. So it is no longer used here. Okay, number, the least significant bit is vacant. So we put a 0 in this least significant bit. Now it is very important to understand that this 0 that we have put here is not brought from the most significant bit. So we have not brought this 0 into the least significant bit. No, this 0 has been lost. It has discarded, and we have put a 0 in the least significant bit. Now if we look at this number, let us calculate what is the decimal value of this. This is in the position weight 1. The weight of this bit is 2, 4, 8, 16, 32, 64, and 128. Since the bits here are 0, we ignore these values. So the bit value here is 1, so 32. This is 0 bit, so we again ignore 16 here. We have bit 1 here, so 8. So 32 plus 8 is 40. 40 plus this 4, 44, plus 2, 46. Again this bit is 0, so we strike off this V. So the new number that we get here, the decimal equivalent of this is 46. So you can observe that the original number was 23. When we shift to the left by 1 bit, we get the new number 46, and this we can see is 23 2 times. That means the original number 23 has been as if multiplied by 2. So a left shift by 1 bit is equivalent to a multiplication by 2. Let us take the next example where we carry out the left shift by 2 bits. So we have the same number 000101111. We know its decimal value is 23. Now we will shift this by 2 bits. So here is our least significant bit. This least significant bit, we will shift it by 2 positions to the left. It comes here. The next bit will come here. So this was my least significant bit coming into this position. This bit is transferred to the next position, 2 bits to the left. Now we are on this one. We shift it to this higher position. The 0 bit is shifted to this position, 2 bits to the left. 1 bit is shifted here, and this 0 bit is shifted to this position. Now observe that this 0 and the 0 which is at the most significant bit, both these are lost. They as if fall off, or they are discarded, and we ignore these. And now what happens in the positions at the extreme right? Both these positions which remain vacant will now be filled up with 0. Let us consider this number. What is the value? The weight of this bit is 1, weight of this bit is 2, this bit 4, 8, 16, 32, 64, and 128. So since the bit here is 0, we strike off, we don't use this. 64 and 1, so this is 64 into 1, that is 64. Similarly, this 32 value we strike off because the bit value is 0. Then we have 16, 1, 8 multiplied with 1, 4 multiplied with 1, and this 2, since the bit value is 0, this will become 0. 1 into 0, 0. And so what are we left with? We are left with 64 plus 16, that is 80, 88, 88, and 4 is 92. So this value that we get is 92. Now if you observe this, this is equivalent to multiplying the original number 23 with 4. 4 3 times is 12, 2 with a carry of 1, 4 2 is 8, and 1 9. So here is our conclusion. A left logical shift by 1 bit, this is what we did in our example 1. A left logical shift by 1 bit is equivalent to, we can say it is equivalent to a multiplication by 2. A left logical shift by 2 bits. Now we are shifting this to the left by 2 bits. It is equivalent to, we saw, this is equivalent to a multiplication by 4. But this 4 can be written as 2 raised to 2. So 2 raised to 2, and this 2 here represents the number of places shifted. So the number of places by which the bits were shifted. And therefore, in general, a left logical shift by n bits is equivalent to a multiplication by 2 raised to n. This is multiplication by 2 raised to n. So a left logical shift operation is basically a multiplication by 2 operation for every bit that we shift to the left. Let us now see the right logical shift operation. We consider our original number to be 20, and this number 20 of decimal can be written as 10100. We have represented this number 10100 in 8 bits. So let us start. Here is from the least significant bit. If we start writing 001, so you have the least significant bit 001 followed by 01. So we have 001 followed by 01, and since these 3 bit positions are not given in our original number, we pad them with zeros. Now let us carry out the right logical shift by 1 bit. Now observe, if I have to shift these bits to the right, I will start with the most significant bit. We'll start with the most significant bit. So the bit which is at the extreme left, or the most significant bit, will be shifted by 1 place to the right. So this bit will become now 0. So we have shifted this bit. The next bit is shifted again by 1 place to the right. This becomes 0. This 0 is transferred to this bit position. 1 is transferred by 1 place to the right. 0 we again transfer by 1 place to the right. 1 is shifted to the right by 1 place. This 0 comes here, and now observe this. This 0 which is at the extreme right, or the least significant bit, this falls off or it is discarded. This is discarded, and so we cannot account for this now, and the most significant bit is filled with 0. So again we must remember, it is not that this 0 is put into the most significant bit. No, this 0 falls off, and what do we put here? We put a 0 in the most significant bit. Now if we calculate what is the value of this in decimal, let us see. The decimal value of this position is 1, the weight of this is 2, 4, 8, 16, 32, 64 and 128. So again, all positions where the bit value is 0, we strike off those values, and we are left with 8. Again, this is bit 0, so we discard it. 8 and 2, 10, and this is again discarded. So this new number that we got is having the decimal equivalent value of 10, and we can see this 20 divided by 2 is 10. So a right logical shift by 1 bit results in a division by 2, and therefore we have this final value here 10. Now let us carry out the right logical shift by 2 bits. So again our original number is the same. We will start with the most significant bit, and we will shift it by 2 places. So its original place would have been this. This would have shifted it by 1 place to the right. So we shift this by 2 places to the right. So the 0 comes here. This 0 appears in the next position. This 0 appears in this position. The 1 appears here. This 0 appears here. 1 appears in the least significant bit, and now observe this. This 0 and this 0 both these zeros, they will fall off and they will be discarded, and the positions which are now unfilled at the extreme left, these positions will be both filled with 0. And now let us consider what is the decimal equivalent of this. So here is the bit value 1, this is the bit value 2, this is the bit value 4, and since all these bits are 0, we can ignore writing the bit values. And now what happens? Since this bit value is 0, we can strike off this, and now the decimal equivalent is 4 plus 1, 5. And you can see this 20 divided by 4 gives us 5. So here is our conclusion. A right logical shift by one bit is equivalent to a division by 2. A right logical shift by 2 bits is equivalent to a division by 4. But that can be written as 4 can be written as 2 raised to 2. So this 2 is the number of shifts, number of positions by which we shifted. And in general, a right logical shift by n bits will be equivalent to a division by 2 raised to n. So these become the important conclusions from this example. Now let us consider a very interesting example where we have to shift the bits of a number which is negative. So we are given a number -6 in the decimal system. This number we know can be expressed in 2's complement as 1010. This is in the 2's complement. This 1 bit here indicates to us that this number is a negative number. Now observe the important change that comes in this example. We are now carrying out a right shift operation, but this is called as a right arithmetic shift. Now what is different in this? Let us understand. We'll shift one bit to the right, and the way it will start is this. We will take the bit 1. This bit will be shifted to the right by one position. This bit is shifted to the right by one position. This bit is shifted to the right by one position. This bit, which is the least significant bit in our original number, it is lost. But observe this part. Since our original bit 1 in the most significant bit position, this 1 was used to indicate the sign of the number. That means this indicates that our original number is negative. So we cannot afford to lose this bit. And so what we do is, to preserve this bit, to preserve the significance of this, we copy this one value in the most significant position. So in my part, in the B value, we have most significant bit is still 1. So the bits are shifted by one position to the right, but the most significant bit is copied into the MSB part of the new number, and the least significant bit is lost. So this becomes our new number. Now if you calculate this, you will realize that this number is nothing but the 2's representation of the number -3. So this is the representation of -3 in 2's complement, and which tallies with our calculation. If when you divide -6 by 2, of course we expect the result to be -3, and that's what we'll get. The only thing is that this number that is given to us is in the 2's complement. So why do we need a right arithmetic shift? So if you observe, this shift was similar to the right shift, the right logical shift. The only difference that came up was this most significant bit, which is 1, is copied into the result. So why do we need a right arithmetic shift? The right arithmetic shift is used to divide negative integers. We have to divide negative integers when the most significant bit is the sign bit. We know in the 1's complement, this bit is the sign bit. Okay. Now, what can be the simple summary of this? A right arithmetic shift of one position moves each bit to the right by 1. The least significant bit is discarded. We saw that the least significant bit is lost, it is discarded. And the vacant most significant bit, this was our original vacant most significant bit. It is filled with the value of the previous MSB. So this one MSB is copied into the new number. So this preserves the sign, and we have also been able to achieve the division. Let us now consider the shift operations on fixed size numbers. We know that a computer can represent numbers in fixed sizes. So as we said earlier, that a word is made up of 2-bit bytes or 4 bytes or 8 bytes or 16 bytes, and therefore the number of bits that can be represented is fixed. If in carrying out a shift operation, for example in carrying out a left shift operation, certain number of digits or certain number of bits are added to the right, then certain number of bits must also be discarded at the left, because ultimately we have a fixed number of bits in a word, right? So let us take as an example an unsigned number, and our number is 0000 and 1110. We can shift this number to the left by one place. So let us write our original number 0000, then we have 1110, and in decimal this number is of course 14. This is the least significant bit of the number and the most significant bit. Now let us see what will be the result when the number is shifted to the left by one bit. So this 0 occupies this position, the 1 here occupies this position, this one occupies the next higher position, this one occupies the next higher position, the 0 here comes into the next higher position, this 0 will be brought here, this 0 occupies the most significant bit of the new number, and this most significant bit is lost, it is dropped off, and therefore this position that we have is now filled up with a 0. Now let us check what is the decimal value of this. This is 1, the weight of this is 2, 4, 8, 16, and since these bits are 0, we need not write the weights here, but if we had to this would be 32, 64, 128, but since the bits are 0, we can strike off these values, and therefore the number that we get is 16 plus 8, 24, plus 4, 28. Again these two bits can be removed, and therefore the number that we get is 28 of decimal. This is of course consistent with what we said earlier, that a left shift by 1 is equivalent to a multiplication by 2. But let us consider an example of another unsigned number. Okay, now in the previous example, of course, this bit MSB 0 that was there, this was a 0 bit. It was not a significant 0 because it was at the extreme left, and therefore there was no change in the result. Our results were consistent, right? But let us consider an 8-bit number. This number is 10100101. We shift this number to the left by one place. So let us write our original number 10100101. This negative number is minus 37. It is in the 2's complement. This 1 in the most significant bit tells us that this is in the 1's complement. Let us now carry out a shift operation, a left shift by 1. So we can see a left shift by 1 will bring this bit to the higher position. The 0 comes into this position, 1 comes into this 0 occupies the next higher position, this 0 is in the next higher position, 1 shifted here, the 0 is shifted here, but now observe something very interesting. This bit 1 is lost because there is no position to the left, so this bit is lost. But remember, this was supposed to have been the sign bit, and we have of course put a 0 in the least significant bit position of our new number. So if you look at this result, we find that 1 which was an indicator of a negative number, that has been lost, and this number that we get now is become a positive number. So this is of course a loss of data which is undesirable. Now let us summarize these rules of left shift and right shift operations. A left logical shift by one position will shift the bit to the left by 1. The most significant bit is lost and the least significant bit is filled with 0. This is what we saw in the first example in this video session. A right logical shift by one position will move each bit to the right by 1. Now, since we are moving to the right by 1, the least significant bit will be pushed away or it will be lost, and the vacant most significant bit will be filled with a 0. A left arithmetic shift. This is identical to a normal left logical. So a left arithmetic shift of one position will move each bit to the left by 1. So the least significant bit will be again filled with 0 and the most significant bit is discarded, and this is identical to the left logical shift. But let us check what happens to the right arithmetic shift. We saw in the earlier example that a right arithmetic shift will move each bit to the right by 1. The least significant bit will be of course pushed away, so it is discarded. But the most significant bit, because it contains the digit 1 or it may contain a digit 0, and these bits are important. So the most significant bit of the new number is filled with the value of the previous most significant bit. This is the important difference between a right arithmetic shift and a right logical shift. Arithmetic shift operations are used for carrying out division or multiplication of an integer variable. A left shift is equivalent to a multiplication by 2 raised to n, and n is the number of shifted bit positions. So if you were to shift to the left by 2 bits, it would be equivalent to multiplication by 2 raised to 2, that is 4. The result of a right shift operation, on the other hand, is a division by 2 raised to n. So n is again the number of bits through which we shift the values. And this is an important one. If the leftmost digit is significant, for example, in a negative number in the 2's complement representation, if the leftmost digit is significant, shifting the left no longer multiplies by the base b. So the base b is of course 2 in the binary system. So if the leftmost digit is 1 and if we shift to the left, this leftmost digit will be pushed off on the left and it will be lost. So shifting left does not imply multiplication by 2 in all cases. These are the important rules that we must remember when carrying out left and right shift operations.